Morning, everybody. Start with any questions on the homework. I guess I forgot to push one of the data sets to GitHub until last night, but it's up there now for the second part.
I just had a question. I was trying to figure out how to print the incorrectly classified numbers.
So for that, you can get the predicted value and the true value, and then you can. I think you should be able to do something like. Well, if you do. Like this would give you a vector that has true entries everywhere that's that they don't match, and then so you could do like X, and this would give you only the rows where the predictions are don't match. Does that make sense? So you've seen lots of examples how to do all the predictions. It gives you a big vector, right? And this is just element-wise comparison, and then this is like a filter. So we're going to play more with the handwritten digit data set today, because that seems to be most of what we do now. But we're going to do it in a very cool, very like last 10 years, like blown up, super popular way. Today we're going to talk about called convolutional neural nets. And these are basically a way of training big neural networks that operate on image data. Okay, so we'll see why we have to try to come up with some clever strategies to deal with the scale of this problem. So let's imagine I have my input is an image. How many entries am I going to have in my input layer? How many different inputs am I going to have if I'm taking an image? 1 per pixel? At least 1 per pixel. So it could be, if it was 1 per pixel, what would that mean? Grayscale, probably. Because so black and white would mean only, it would be like binary, 1 per pixel. Grayscale would be continuous, 1 per pixel, right? If I have a color image, it's probably like 3 per pixel, right? And the number of pixels is width times height, right? So the D there will be is like the depth, the color depth, how much information per pixel I have. So if I have a pretty small image, like 1,000 by 1,000 pixels, right? I have 3 million, a 3 million dimensional input vector. Okay? That's a 1 megapixel image, right? That's like, your cell phone camera laughs at that. It's terrible. Okay? So even a small image, that's like 3 million potentially inputs. Right? And let's say we want to connect it to a hidden layer. Just have a dense hidden layer. And let's just say it's of like the same size. How many weights am I going to have to train to connect these two together? Well, it's going to be my number of inputs times my number of hidden nodes. Okay. And if they're the same here, and I start with 3 million, I end up with 9 trillion weights. that's going to be a tough problem to solve. Right? There's basically no way I'm going to be able to train a trillion, almost 10 trillion weights. Right? So I, can shrink. I'm going to have to shrink my hidden layer by a lot. But if I shrink it too small, then I'm probably not going to be able to capture all the information I want and come up with as complicated a model as I'd like. Right? So when I'm dealing with image data, I really like, some clever way to avoid this problem where I have just weights for each input being connected to my hidden layer, right? Because I have so many inputs, right? It's just going to be too many weights. So a convolutional neural network is a way to cut down on the number of weights I have to train by a lot, by like orders of magnitude. And it's based on, so the idea here is we basically say, okay, what did computer vision people do before we had neural networks? Okay, let's take the hard work that those researchers did for like 30 years, and let's replace that by neural networks. And so that's kind of the idea. So we take classical computer vision algorithms, and we replace them by a neural network that kind of does that operation for us, and then we put it together with the rest of the neural network, and we get a convolutional neural network. So let's talk about what researchers, what people used to do to do image analysis tasks. So let's say I am trying to write some computer vision code that detects squares in an image. Okay. So like basically if I have 4 edges that are perpendicular to each other, then I would say yes, this picture has a square. So the way that a lot of these algorithms work is they make a small little filter that looks at just a few pixels at a time, and we take a dot product. So we look at all the pixels in an area, multiply the image values with the filter values, and add them all up. Okay. And the resulting number we get basically says how much does this little window that we're looking at look like the filter pattern that I started with. Okay. So as a concrete example, if I wanted to detect vertical lines in my image, I might have a filter that's a little 3x3 region of my image. Okay. And these are going to be, colored, and these will be white. Okay. And to figure out where there are vertical lines in my image, I'm going to slide this over the whole image, and for each 3x3 little patch, I'm going to multiply what's here by what's here and add up all 9 pixels. Okay? And then I'm just going to output like the sum that I get. Okay? So if I do that to this picture I have here, the output that I will get is, so these 2 vertical lines are going to be, they match that well. So my output here is going to be, have these 2 vertical lines where I detected them in the image, and nowhere else matches. All right, so like this doesn't match my filter, so my output is going to be small or close to 0. So maybe like where there's some points where I get a lower response, but I'm going to really output high values where there are actually vertical lines in the image. So this is one like filter, okay? And And right, I just slide this little window across all the little 3x3 blocks in my picture, and I find the parts where they match, right? And those are going to be high values of output, and the parts where they don't match are going to be low. Okay. So this operation is called convolution, which is where the name convolution neural nets come from. Okay. But that's the idea. We take these little patterns and we slide them across the whole image, and just output basically how much each little neighborhood matches that filter. Okay. So the kind of nice thing about this is I get information about the whole image here, right? But my filter here is actually really small. There's only 9 values in here, but I'm using those same 9 values everywhere in the image, right, to get this out. Okay. So what computer vision folks used to do is come up with, the best set of filters they could. So maybe, I care about detecting edges. My filters might look like this. Okay. Maybe I have 4 filters that detect edges in whatever directions. Okay. And so when I run these over my image, I get these new sort of activation images. So how much this picture matches each of these filters in each spot. Okay. And that gives me a more abstract representation of the picture I started with, and I can do that helps to do more like analysis or prediction with the image. Okay. So we're kind of like maybe this is some beautiful full color image, and these filters, like, okay, now it's just where the edges are, right? That's a much easier thing to work with, and then I can use other algorithms to try to figure out if I have a square or not. Okay. I can repeat this a bunch of times, right? So maybe once I have this, I'd use the same filters again and maybe scale it down to see if I can make the problem smaller, or but I can use these sort of filter activation images to help with my whatever image problem stuff I'm dealing with. That sort of makes sense. So it's not, we won't go too much into what you actually do with these images once you get them, but this is kind of the mechanism that we use to transform the images into something simpler. Question?
So is this kind of like PCA, where we just figure out some dimensions we don't need?
No. So in this case, the output is going to be basically the same size as the input, and it's I would say it's not necessarily like PCA. So there is maybe some filtering, but I wouldn't think of it as like PCA really.
So we're just using those different filters to filter out, to reserve the properties we need.
More like detect, right? So here, I don't know where the edges are, right? But after I apply this filter, I see oh, here's where the edges are. So it's more like figuring out where stuff is, as opposed to filtering other stuff out.
So it's like we have some features already, with the layer node.
To start with, we just have the pixel values, right? The brightness at each point. And so we're transforming the image of where is it bright in the image to where are there edges in the image, right? And that's it's potentially a more useful kind of information. Yeah.
Is there equal values all of the weights, all of the filters, or can they have weights as well for your output?
So usually, so we'll probably get a separate output for each one of these.
You'll get one for each one.
Yeah. So we'll see when we do the neural net version of this what that looks like. Okay. All right. So so the idea here is computer vision people, they use these little filters, they slide them across the image, and that tells them something useful that they can use to do more analysis. Okay. So our solution to this huge number of weights that we're dealing with is to use this approach. And what we do is we have, we learn these filters, we train a neural net to come up with what these filters should be, and then use those in our network. So a convolutional neural network, I don't know how best to draw this. So I'm going to draw, so I'm just going to draw one of these filters, kind of what it would look like. So basically, I have this little 3x3 filter, and there's a weight for each one of these things, and the weights kind of are going to control what this filter looks like. Okay, so I have a weight for each, pixel in this filter. Okay. So here, my little 3x3 filter, there's going to be 9 weights. Okay. What I do to run an image through this layer is I look at each little 3x3 neighborhood in my image, and I run it through this filter the same way I did over there. Right? The only difference is instead of handcrafting these filters based on whatever I forced my grad students to do for years, right? Now the weights are going to be, I'm going to train them with the training techniques we talked about yesterday. Okay. So what I'm going to do is for each neighborhood, I'm going to take 9 at a time, run it through here, get an output. I'm going to take 9 at a time, run it through here, get an output. Okay. And I'm going to get basically an image of the same size, but instead of the values corresponding to the brightness, the values correspond to how much each neighborhood matches this little filter. Okay. So the cool thing about this, the reason that it is useful, is that I have, say, 3 million dimensions here. I only have 9 weights. Right? So no matter how big my image is, there's only 9 weights that I'm messing with here. Right? So this is going to scale really well. It's going to be actually possible to train this. Okay. Yeah.
So just to solidify my understanding, so at are we still using perceptrons here?
So this one, there's probably not perceptrons, or they're not the same as we talked about. So this, that's a good question. When we look at the code, I'll verify. Actually, I think. Oh yeah, so there is still an activation function. So yeah, so this guy is basically like a 9-input perceptron, and the 9 inputs are a 3x3 neighborhood of the image. Okay. All right. So this is a convolutional layer, and it takes an image, a 2D image. It applies this filter, and it gets out another 2D image where the values correspond to like how much each little patch matches this filter. And I can have a whole bunch of these, right? So I can fit, 10 or 50 or 100 of these in my layer, right? And so I'll get out each pixel. Each neighborhood over here will have an output for each one of these filters. So I might be increasing the number of outputs if I have more than one of these in my layer. still the number of weights that I'm training is very small. And I'm only training, 9 weights per filter, regardless of the resolution of the images that I'm working with. So the savings comes from the fact that I'm reusing the same 9 weights on every single neighborhood of the image, right? And that's going to make things work efficiently. So yeah, we're taking the old school computer vision stuff of designing these filters and applying them, and we're just going to machine learn what these filters should be, right? So A, I don't have to design them, and B, they'll be, if I do a good job training, they'll be like the best ones I can pick for my particular image data set that I'm training with. Okay. So that's a convolutional layer, right? We train these little patches that we apply all over the image, and we get out this abstract image. All right. So the next kind of trick we add to speed up the training and make things a little bit more tractable is we want to reduce the dimension of our data. So this is a convolutional layer. We add another type of layer which is pretty useful. It's just called a max pooling layer, or a pooling layer. And basically what that does is we just look at 2x2 neighborhoods, and for each neighborhood we output the max value that we see. Okay. So if my neighborhood has values A, B, C, D, we just output the max of these. So if I have a 2x2 pooling layer, then I'm reducing the number of reducing the outputs by 4. Right? For every 4 inputs, I just have 1 output. Yeah. And so this makes it I'm downscaling my image. Yeah.
Would you do like pre-processing on the image, like a color image?
Yeah, so it depends on what you're doing. The networks that we're training, and I think probably in general, the input format is kind of rigid, right? So for the ones we're training, like they have to be 28 by 28 grayscale images. So I think you'd have to do pre-process beforehand to make sure it matches. I think in general it would be hard to write a neural network that is totally where the input size is variable. So I think you would have to pre-process and just scale it to the right size ahead of time. So these are the two layers that we're going to use in addition to what we already saw. Okay. So if I want to make, let's say, a classifier for an image, I might come up with a network that looks like this. I have my input layer. I have a convolution layer. Okay. And so here I have a bunch of filters. I can pick whether they're 3x3 or 5x5 or whatever. I can pick how many of them I want. So and I get to pick that. And then I might run this through max pooling. Okay, so I'm going to downscale. Okay. And then maybe I have multiples of these. So as I add more of these convolution layers, I'm getting these like more and more abstract information about my image. And then maybe after this, I just have some normal dense layer. I've downscaled stuff by a lot, right? So now, you know, I can fit a dense layer in here, and then maybe I have. And so this is an example of a network you might use for like an image classification task. Yeah.
So we're using images a lot. Are there any other applications this would be used in?
Anytime where there's where the proximity of the data matters, right? Because we're looking at neighborhoods, right? So this could be data that is time series, where things that happen close in time, you know, there's important information there. So you could use it for a time series data. Okay. So another thing we'll talk about is when we have classification. We somehow need to handle having a whole bunch of different classes. Right? So for the digits, right, we have 10 output classes. Right? So I could just try to have one output that goes from 0 to 10, hopefully. Right? Is that going to be a good idea? So I just have one output of my neural network. It says 5.5. What does that mean? Could mean that it looks like a 5 or in between a 5 and a 6, but what if you know, what if I have something that I'm not sure if it's a 5 or an 8? What do I output? Do I output 7? Right. So why is outputting a single you know, a single value that ranges from 0 to 10 not a good idea here?
It seems like you have to make a system really can you classify like 5.1 as a 5 is classified as a 1?
Yeah, so it's unclear what anything that's not like a perfect classification means, right? So my outputs are the numbers, or the digits 0 through 9. Is it really, am I really outputting numbers? And really what I'm outputting are categorical labels. Right? They happen to be, they happen to correspond to the digits, but they're not sorted. They're not, right? There's not really any relationships between them. They're just labels that happen to be numbers, right? So having, outputting a numerical value really doesn't make sense in this case. They may as well be, I may as well be outputting plus times, minus divide symbols. It doesn't make, I could try to come up with like a 0 to 4 encoding for that, but that doesn't really make sense either. Yeah. So what would be an appropriate output of my neural network when I have 10 classes that I want to distinguish? So I probably want to have one output per class, right? So I'll have, a 0, a 1, 2, 3, 4, 5. And so I could, just take the max of whatever comes out, but it would be really nice if I could somehow force these to be a probability. Right? It's nice to think about probabilities. Right? And so the activation that we use for that is called a softmax. Yeah. And the idea is basically we just have an output for each one, And then the probability is just e to the I take the it's like an average of all the outputs, but with this exponential weighting thing here. So all of the outputs are going to sum to 1 when I finish this, and they're kind of scaled, so the biggest one is the highest probability, with some scaling to kind of make things work better. So basically, this is just this is called the softmax. The equation is not super important. But what it does is it just takes 10 outputs and converts them into probabilities based on their relative values. All right. So for digit classification, right, we're gonna have some of these layers. At the end, we'll have a softmax that'll tell us the probability that our input is each of the digits. Okay. And the last thing we'll talk about is related to training. So we talked a little bit yesterday about batching. Does anybody remember what that idea was there?
Isn't that shrinking your data set and then running it through each of them, and you do an epic every time?
Yeah. So instead of pushing one image through, tweaking the weights, pushing one image through, tweaking the weights, pushing one image through, tweaking the weights, that's going to be slow, and it's also probably going to overfit and have all sorts of noise and stuff. Okay. So what we do is we take a whole group of images, so maybe like, so the data set we're working with has like 60,000 training samples, so we'll run them through like 200 at a time. We run through a whole bunch of images, we look at the errors at the end, and then we update the weights. So we run through a whole bunch of examples and train the weights based on the output of a whole bunch. So that's batching. So it improves efficiency, right? Because we're running through a whole bunch of examples at once, and it can help mitigate, overfitting and that kind of stuff. Another trick that we can use in training to avoid overfitting is called dropout. Okay. And it's basically like, call it alcohol for neural networks. And the idea is, as we're training, we just pick a random number of nodes, and we just turn them off for that training step. Okay. So I'm going through here, running through here. If I'm adding dropout, maybe just like 10% of these nodes are just turned off and the output 0. Okay. And so if we do this, then all of the neurons kind of have to work together, because the individual ones might get turned off, right? And we want the network to still work even if it's turned off. Right? So the dropout kind of like gets everybody on the same team and makes sure that they work together even if some of the neurons are lazy for one step. Okay. So dropout is another technique to improve training. We just turn off some percentage of a random set of the neurons at each step to try to prevent overfitting. Yeah.
So this is like what you were doing yesterday, where you run it, you notice the bold, like some lines are bold, some lines were not bold, you try to get rid of the ones that weren't. Is that kind of what it's doing automatically?
No, because that was an intentional thing where I looked to see what the weights were before I removed them. This is, they're just selected randomly. It doesn't matter what the weights are. And it's to kind of spread out spread the load across all the neurons is kind of the idea. Yeah.
So I thought yesterday when we were talking about a batch, it was we little bit unit the size of our sample and keep training the weights on different set of those units until we look through several epochs. So that feels kind of like dropout, except that it is not random.
So when we're batching, we're using a subset of the inputs. When we're doing dropout, we're using a subset of the neurons. So the dropout is like we have the same data, we just ignore some of the neurons in the network. So they break temporarily.
So they are both kind of like anti-aliasing stuff.
So the batching is kind of necessary because so for the batching, there's kind of two extremes. We could run one example and update the weights, right? And that's going to be like pretty noisy, right? Because if I have an example that is misclassified, I'm going to like wreck the whole network, and then the next ones are going to try to fix it, right? And so running one example at a time is going to be like really noisy, inefficient training. On the other hand, if I try to run through all of the examples and update the weights for the whole data set at once, I have to feed all 60,000 images through just to update the weights a little bit, and that's also going to be really efficient. It's going to be stable, right? I'm not going to do drastic changes, but it's going to take me so long to do each update that it's going to take forever to converge. So the batching is a compromise between feeding in enough data at a time to be resistant to noise or a few bad examples in the training set, but to be small enough that each weight update is pretty fast. So I get through a whole bunch of optimization steps. So that's the compromise there. The dropout is really about it's regularization. It's trying to penalize or avoid having really high weights in the network. Right? If I have one neuron that's like doing all the work and has really high weight, and then I drop it out, then I'm going to get a really bad prediction, right? And so the dropout is going to adjust the other neurons to compensate, and then it'll tend to reduce the weight for like the heavy or like really important neurons. Yeah.
What are the downsides of having heavy weights?
Yeah. So generally, like sensitivity to outliers would be if you have a big weight, right, it's going to be really sensitive to whatever the input is. And so probably you don't want that. I guess a high weight is probably also a sign of overfitting. So you're like working really hard to like match some data, and so it's kind of a sign of overfitting, or can be.
Is it doing dropout kind of like lying to yourself?
Yeah. I mean, it seems like a crazy idea, but it is like it works really well as a regularization to try to spread out the load across the whole network. That said, for the example we'll look at, we didn't need dropout and it made things slower, so our analysis will look at, we won't consider dropout. But yeah, it is an important part for like a lot of real networks. Cool. So any other questions about this concept? Right, so we want to run neural networks on images, but we don't want trillions of weights. So if we use convolutional neural networks, we can get down to like, the convolutional layers will be like hundreds or thousands of weights, which is much more palatable. Yep.
When you said slower just now, by adding dropout, does that just mean it takes longer to convert to a low layer solution?
No, for this person, each training step took longer. So I ran the same number of training steps, and it just took longer to finish.
So why would that be?
I suspect it's just extra computation that had to be done to like pick the random ones. Or I kind of assumed it would it would end up being less work in the training, but it seems to be more work. Right, cool. So let's take a look at some code. So we are going to use a library called Keras. To run this, you will need to install Keras and TensorFlow, which you can do through pip. It should just be pip3 install Keras and TensorFlow. So how many people have heard of TensorFlow? So it's Google's big open source library for training neural networks. It is not pleasant to work with. It's really low level, and I'll show you the corresponding TensorFlow code to the code that we're going to write in Keras. Keras is a much friendlier layer on top of TensorFlow. It can actually use other backends. So I can write Keras code, and I can either use TensorFlow to do the training, or I think PyTorch or a couple other backends. So I just write my network at a high level, and Keras will figure out how to turn it into TensorFlow operations and whatever for me. So it's much nicer to work with. So now we're getting into like a bigger amount of data. For these examples, it took like 5 minutes to run the training. And it's a relatively small data set. So as you can imagine, as you get larger, right, it's going to be just bigger and more time training. But that's on my laptop without a real GPU. So if you had a real GPU, it'd be faster, but still, like, we're getting into these are really heavy computations. All right, so what we're going to do today is we're going to do, shocker, digit classification. This is just a really, really good data set, so that's why we use it all the time. So I have Keras. It has this MNIST data set built in, so we can import that. And so it splits it into training and testing. So for this one, we'll have 60,000 training examples and 10,000 testing examples. And you see here, Keras has decided that it's going to use TensorFlow because I don't have any of the others installed. So every time I actually do training or prediction, whatever, it's going to be running TensorFlow stuff. So just to remind you what this looks like, we have a bunch of these digit images. These are higher res, and they look a lot easier to classify than some of the other ones we've seen. But and these are each 28 by 28 pixel images. So these are the first data set we looked at, I think, was just 8 by 8. So these are much higher res. And much more data, right? So we went from 64-dimensional data to like 1,000-dimensional data, close to it. So that's an order of magnitude jump in the data we're looking at. To make this, to make our machine learning stuff happy, we're going to reshape this. So instead of having I guess a lot of this convolutional stuff, the last dimension is like the color in the pixel, and for grayscale, it's just a one-dimensional thing. But if we had color images, then the last dimension would be third. So basically, what we're doing here when we're reshaping is we're adding an extra dimension that does nothing. Right? It's just like, so we have a 28 by 28 by 1 thing for each picture instead of 28 by 28. Right? That's just to make the dimensions match up for all the training stuff that we can do. Yeah, if you write code like this, you're frequently going to get errors about dimensions not matching. You say, oh, I expected a 4-dimensional array, and you gave me a 3-dimensional array, and you realize, like, oh, I just have to add a dummy dimension or be prepared to deal with that. As we talked about, we're going to have 10 outputs, which correspond to the probability of being each of the digits. Our training data is not in that format, right? So the y's of our training data right now are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And so that doesn't match up with that at all. Okay. So the first thing we're going to do is we're going to convert our data to what's called the one-hot representation, which is basically we're going to convert it into the probabilities. Right? So if I have a 4, the probability of it being a 4 is 1, and the probability of everything else is 0. So I'm going to take my 1 point and I'm turning it into a 10-dimensional, or a length 10 array, and there's going to be a 1 in the correct spot and a 0 everywhere else. So that's called the one-hot representation. There's going to be a one hot value, and then the rest are all zeros. So that's what we're going here. So we're going to do 2 categorical. So it just looks at how many different values there are, assigns, and then turns each y into an array with the appropriate value set. So if we look at this, so this is a 5. So my one-hot representation is 0, 1, 2, 3, 4, 5. This entry is on. All the other entries are off. So this is my training data converted to the one-hot representation. Yep.
If you had noisier data, you see 0 values.
Well, so this is training data that's labeled. So I'm not aware of any data sets where the labels are like the ground truth labels, or I don't know. So I could.
I used to wonder why we need float there.
I think that's just the default. What we compare to is going to be floats. Yeah. Yeah, you could imagine having a data set where like the human that work on the training data is like, well, that could be a 5 or a 6. So maybe put it at 50-50, but I'm not aware of. You'd have to change the representation here, right? To start with, the y's are just, are just the number that it corresponds to. So you'd have to have some way of saying the likelihood. So this is our one-hot representation, right? We just transformed the 5 into 0, 0, 0, 0, 1, 0, 0, 0. So now we'll go ahead and build a model. So we're going to use the Keras library. So the model is going to be a sequential neural network, which just means it's one of the feed-forward networks that things go from layer to layer to layer to layer. And so we just, and the way we build this is we just add the layers from the input forward. So we're going to start with a convolutional layer. Okay. So our kernel size is 3. So what that means is we're going to look at, this is going to be 3 by 3 patches. Okay. We're going to use the ReLU activation. So once we sum up the output, we're going to throw away any negative values and just set them to 0. Okay. This is my input shape, so they're 28 by 28 by 1. Adding the by 1 seems dumb, but whatever. And we're going to fit 64 of these. So we're going to find 64 filters in this layer. So the output from this layer is going to be, so our input is 28 by 28 image. Our output is going to be 64 28 by 28 images. And so we're going to output one output per filter that we train. And each one of those is like a whole image. It's actually not quite 28 by 28 because we have the 3 by 3 images around the edges. We throw those away. So where it's actually going to be 26 by 26 image because if our filter has to go outside the boundary, we just don't use it. So we're actually shrinking the image. Yeah.
So why did we end up choosing 64? I noticed we have it in the next convolution.
This would be the black magic, is figuring out how many do I need. I'm using 64 because the documentation that I looked at uses 64. So, I'll show you another example where we just used 5, and that seemed to be okay. So this is probably overkill, but who knows? Yeah. So this is our first layer. We're going to do this model. Will do the first model will be pretty simple. So after that, we're going to do 32 filters. Okay, so we're going to look at 3x3 patches again, and this time we're going to have 32 outputs. Then after that, we're going to flatten our model. This just takes our 2D thing and just puts it into a 1D array. So it does nothing. This is reshaped basically. And then we're going to have a dense layer with the softmax activation. There's going to be 10 outputs here. So our flattened convolutional thing, we're feeding into 10 neurons, and then we're going to use the softmax to make sure the outputs here are probabilities. Okay, so this is our model. So it's going to be 1, 2, 3, basically 3 layers. Yeah. So questions about how we kind of built this up? I mean, the obvious question is, how do you know what layers to use? And that is like, you look at what other people have done and you experiment. That's really the answer to that. All right. So then we're going to compile our model. So this basically sets up the TensorFlow code that's going to be run when we train it. So here we're going to use the atom optimizer, which is it's the gradient descent with some extra stuff to make it better. We're going to use this categorical cross entropy. So this is how we measure the error. And basically, instead of just looking at right or wrong, we're going to look at the probabilities that we output. And wrong and confident is really bad. Right and confident is really good. And not that confident is somewhere in the middle, right, whether we're right or wrong. Right? So basically, this looks at this is a way of just kind of measuring how our probabilities match up with what we expect, right? And we eventually want all of our predictions to be confident and right, but this kind of smooths out and pushes us away from the wrong and confident predictions fast. So this is just this is how we measure how good we're doing. And we're going to print out how accurate we are as we train. So to train this model, we're going to fit it to our training data. We have validation data, which I think this is used just to print out what the accuracy is. It shouldn't be used for training. And we're going to do 3 epochs of training. And if we do this, if you see, each epoch took about 2 minutes to run. And if you look at the accuracy, after the first epoch, I'm already getting 97% accuracy on my training data. It doesn't really improve, so maybe 1 epoch was actually enough here. Yeah, hitting 97% accuracy right out the gate, that's pretty nice. So if we look at a few of these predictions, so we look at just a few of the test samples. So this is my output. It's 10 numbers. So can anybody see what the prediction is going to be? So 7, why is 7? Yeah, so here, these are all like basically 0, right? 10 to the minus 7, 10 to the minus 14, right? Here, this is 0.999999. So this is very confident that this is the one, and if we count 0, 1, 2, 3, 4, 5, 6, 7. So it's the 7th entry, and we're very confident that that this is that this image is a 7. And similarly, like this one also 5, 10 to the minus 5 confidence. This one is less confident, only 96% sure. Okay. This one, again, very, very confident. So, and these are the expected values, and so we see that we are actually correct. Right, this one 7, 2, 1, 0. And if we look at the pictures are 7, 2, 1, 0. The 1, it looks like the 1 was the one that was least confident. And if we look at the picture, you could see why maybe be a little bit less confident, maybe slightly 7-ish. So if we look here, the 4. So it looks like it thought maybe it was a 4. Just a little tiny chance of it being a 4, which maybe you can see from there. There's like a 2% chance of a 4 hidden in there. So, and for these examples, very high confidence on and high accuracy. So, questions about? So it worked really well, but it was kind of slow. 6 minutes for a little bit of digit classification training. I don't want to do that. So what we're going to do is we're going to add some max pooling layers. Okay. So in between the convolution, or after the convolutional layers, we're going to just downscale. And so we're going to take our image and we're going to cut the resolution down by 4. For each 2 by 2 region is going to just be 1 pixel. So we're going to add max pooling, 2 by 2. So we're just going to downsample and going to train it the same way. And we see this time it's almost twice as fast, right? So the second to Emacs took about 1 minute instead of 2 minutes. So, should make sense. We're running way less through our network because we are shrinking the size of it as we go along. So fewer weights to train, less computation to do as we go. Okay. And the accuracy is actually slightly better. So the first network was 97% accurate. This is 98. So, any thoughts about why that could be? It could be chance. If we look at the testing and training difference, so here the training accuracy was like 98, and the testing was like 97.
Overfitting?
A little bit of overfitting, right? So because we had more weights, we were overfitting a little bit. When we downscale it, right, we kind of average out that stuff and we avoid a little bit of overfitting. So, yeah. So I think our training accuracy probably went down a little bit, so 0.982, so there's 0.985. So our training accuracy that went down slightly, and our testing accuracy went up a little bit. It could also be some random chance because there's some randomness in here. So yeah, this is our trained network. Let's see if we can kind of try to understand what's in it. This is hard to do because there's like a bajillion weights, but we'll look at a few different features of the network. So the first thing we're going to do is we're going to look at the weight, the filters we trained in the first convolutional network. And so these are all of the 3 by 3 little filters that I trained, or that we found. And you can see some similarities to like the handwritten ones we made over there. But most of these, like the dark spots, they like kind of match one particular shape. Right? So it's not really obvious what these are doing, but they're sort of related to like the edge filters we were drawing over there, except these happen to be trained by a neural network as opposed to handcrafted. Okay, so like here we're detecting diagonal stuff. Here we're looking at horizontal lines that end. vertical lines, that kind of stuff. So that's one kind of way to visualize. If you have fewer and larger patches, you might see more interesting stuff there. And then the next thing we're going to do is we're going to look at the output of the intermediate layers, just to see what these look like. So we're going to look at the first layer. So we run it through the first convolution, and we're going to look at what the outputs are. So we're going to get 64 outputs, one that corresponds to where, which neighborhoods match each of these the best. And if we look at that, we see that some of these, some parts of the 7 don't match any of these, right? So like these filters, basically none of the image matches those well, right? Whatever this filter was, it matches pretty well over the whole image. I suppose we can. So this particular filter and this filter match like a lot of the 7, which I guess that's like a dark stroke, I guess. So again, these are kind of abstract representations of the 7. This one's kind of weird. It's like a shadow in there. Right. So again, not super easy to really understand what's here. But we're getting like a more abstract representation, and the hope is that the more abstract representation will be easier for the dense layers to handle. So this is the first convolution layer. Then we run it through the max pooling layer. So this is the same as the previous one, except everything is now downscaled so I cut it in half horizontally and vertically, right? And so this is just the brightest pixel in each region is what I kept. Right, so now these images are smaller. And then we'll look at the second convolution layer, right? And these, now stuff's starting to look weird, right? So like somehow there's like just a blur here. I have no understanding of what this means, but that's that's the output of this layer. Right? You can see we're getting to a place where maybe you can understand why the dense layers work better here. Right? They're pretty sparse. Right? It's mostly zeros. Right? And then we have these kind of weird patches, and hopefully you can kind of imagine that is helpful for the dense layer that we view to eventually. Let's go ahead and look at what these filters look like for. See, I think so. These are going to be even weirder looking, I think. So these are maybe a little bit harder to visualize because there's so many of them. There's each of the 64 outputs from my first convolutional layer has 32 outputs from the second. So we have just way more stuff to visualize here, and it's pretty weird. So we'll ignore that. But in any case, right, we've gone through 2 layers, and the outputs that we get are something just really weird. But it is appropriate for the network because the dense layer at the end seems to be able to handle that really well. Yeah, any any questions about what we did here? Yeah.
Is this after the first, is this during the first epoch or after all three?
So this is after all the training is done. Yeah. If we looked, so it doesn't look like much changed because the accuracy was about the same. So I would guess the weights didn't change very much after the first epoch. Other questions? So while we have a little bit extra time, so let's maybe look at another model and see how we can do here. So let's play with the some of the parameters we have to work with here. So we're putting out a bunch of convolution filters. Maybe let's do like a lot fewer, but maybe make them a little bit bigger and see what effect that has. So now we're going just 32 convolution filters of slightly larger size, right? And then 16 in the next layer. So we cut down our number of filters by a lot. Let's see if this is still going to work. So let's see. So things got way faster. So it's going to be about 30 seconds per epoch because we've cut down on the number of weights by a lot. And so again, with fewer filters, there's fewer links in our network. So there's less data to push in when we're training and less weights to train. Accuracy already up to 97%. So it looks like 64 was way more convolutional filters than we needed. Who knew? So it looks like this simpler model is more than sufficient. Yeah, training accuracy. Yeah, 97%. So we basically hit that first model right away. So maybe let's get a little crazier and see if we can go even less. Maybe let's just go 16 and 8.
Yeah.
Yep.
So I imagine like you want to train this model and then use it. How do you store this?
So basically, yeah, we'll look at the output that we get here are basically just the matrices for the weights. So this is the trained model, it's just these matrices. And I guess the topology information, so like what the layers are, but this is what you would store. So these are the biases, so these are the constants that get added into everything. And then these are just the weights. So here I have, these are going to be 16 dimensional filters because we went 4 by 4. So yeah, that's what we get. So maybe let's go even crazier. We already do 16. So this should train even faster. Let's see. So I mean, even to start with, like, the accuracy, is kind of incredible how effective these things are. Cool. So it looks like our first model was way more complicated than it needed to be. It was easy to train, but a little bit slower, right? And these ones. So it looks like I'm not quite hitting the same accuracy. It looks like I'm still
What did you change about?
So now I'm only having 16 and 8 outputs from my convolutional layers. So it looks like accuracy is a little bit lower. Not that much lower. So still remarkably close. Yeah. So these are like, I don't know, one of the coolest uses of neural nets, I would say. It's kind of incredible how well these things work. Any other questions? So the assignment that you'll have related to these will go out, I'm not sure if it's the next one or it's the next assignment. You're going to train these on almost this data set, but not quite. You're going to look at digits in a bunch of different fonts. Or sorry, you're going to look at basically characters from different fonts. And we're going to see what happens as we train them with, so let's say I train on Times New Roman and I test on Arial. Does it work? What happens if I train on Times New Roman and Arial? What happens? So we're just going to kind of play around with these to see like character recognition with these CNNs, how the training, what the data that we train on has an impact on classification. Any other questions? All right. We'll see you on Tuesday. Next week, Varun is going to lecture twice on Wednesday to catch up for that like second week when he was traveling. So he'll have me on Tuesday and then not again for a week.
You just emailed them?
Yeah, if you just email them to me, that's fine. You can send